talk about the code for the BMP180. But before we get into this, I would like to briefly discuss the waveforms for the I2C protocol. I'll be referring to page 20 on the BMP180's datasheet as it explains this concept extremely well. So, as you know, we have our two major lines here, the SDA and SCL. Now these waveforms are shown below. SDA's waveform is here and SCL's waveform is below. When we give a start condition via our code, SCL must be kept high while SDA is low or has a falling edge. You can see this, SDA has a falling edge and SCL has been kept high. At this point, the slave's address is sent and the write/read bit, which is actually this bit here, this bit is contained in an 8-bit byte, and the write/read bit can either be 0 or 1. Depending upon this, the appropriate operation is selected. Now if the slave gets a signal and sees it's being addressed, it lets us know this by pulling SDA low in the ACK part here. So you can see SDA has been pulled low. And at our stop condition here, our SDA has a rising edge while our SCL has been kept high. So when our SCL is high, our data must be kept stable on the SDA line. SDA is our serial data. You can see this, that SDA has a rising edge and SCL has been kept high. So this is just a brief explanation upon waveforms and how these work for I2C protocol. Let's actually determine the addresses for our sensors so that we can begin to communicate with them. So we can either look on our data sheets for the BMP180 or MPU9250 and determine their addresses, or what we can do, we can actually download this code here from the Arduino website. It's called Icrc scanner. There are many variations of this code, but they all do the same thing. What they're doing is they're scanning the A4 and A5, or the SDA and SCL lines, and they're determining what devices are on those two lines, and they're sending us the address of those. So let's open that up and see what we're getting. So we found two devices. In the previous video, we've built a circuit with our BMP180 and MPU9250 both connected. So this makes sense. We have two devices, one with an address of 0x68 and another one with an address of 0x77. Now we know from the datasheet for the BMP180 that our address for that is 77. So let's see what happens when I unplug the SDA and SCL lines for the MPU9250. You can see we've only gotten one device with an address of 77, and that is the address for the MPU9250. So I'm just going to plug these back in. And let's move on to our actual code for the BMP180. So this is our code for the BMP180. The very first thing you want to do is you want to include the wire.h library. Next, now we found what the address is for our BMP180, so I've defined this address as BMP180_address, and these words here will save as the hexadecimal address 0x77. Here I've defined a few variables. Now these variables have been defined as per our datasheet, so let's go on to our datasheet and have a look at that. So all of the variables have been defined in regards to this, so some are normal integers and variables and some are unsigned. So you can see this, AC1 to AC3 are just int16s, while AC4 through AC6 are unsigned variables, so they're uint16s. The same goes for these variables down here, x1, x2, x3, b4, b7, etc. These have all been named as longs in the datasheet, and some are unsigned longs. So I've kept these as int32ts and uint32ts. Now what we want to do, we want to actually determine our resolution. So how accurate and what is the frequency of our data that we're getting from the BMP180. So I've actually put the sensor in ultra high resolution mode, but you can also put it in low power mode. There are many different modes in between. So let's actually flip to that page in the datasheet. Okay, so this is the table for our hardware accuracy modes. So you can see we have ultra low power, standard, high resolution, ultra high resolution. So if you remember in the code, I've chosen 3 and 25.5. You can see this. I've just put 26 here milliseconds delay, and our parameter has been set to 3 here. Now I've set the temperature, pressure, and altitude as a float so we can get decimal values from them. And that includes our variables that we'll be needing. So let's move on to actually understanding what this code here is doing. So the very first step is to begin communication with our I2C device in our void setup, and we will be outputting this at 9600 baud. Next, in our void loop, what we're doing is, this is pretty much what we'll be printing out in our serial monitor. So our temperature will be printing out here, our pressure will be printing out here, and our altitude. How the BMP180 works is actually converting pressure and taking the pressure and converting that to altitude via a formula. So that formula can be found here on page 16. So this is the formula we've used as per the datasheet to get the altitude, but it's important that we get this accurate PO value. You can't just assume that it's 1013 hectopascals, because the weather might be different in your location. So what you have to do, you have to determine PO with this value here. So find your altitude, plug in the pressure, and determine PO. And you want to plug this value into this part right here where I have 968.244. Plug that in and this formula will work for you. So below here in our void loop, I have a few functions. I have our read uncompensated temperature and our read uncompensated pressure. These functions are just looping and refreshing constantly, but we'll get to those later. Here I've created this read to registers function. It takes the address of the register we want to read as an input variable. So first what we'll do, we will begin transmission with the BMP180 by sending out the BMP's address on the I2C lines. Those lines are SDA and SDL. Then we'll use the wire.write code to tell it what register we want to read. Then we will end this transmission to let the BMP know that we are done instructing it. Now it knows that we want information from that specific register, so we hand over control of the SDA line to the BMP180 with wire.requestFrom, which is this one right here. So this numbytes variable which we have here tells the BMP how many bytes of information we'd like to receive. So we can receive any number of bytes. So we've done this because we'll actually need 2 bytes for temperature and 3 bytes for the pressure. So after requesting the bytes, the wired library should have stored this information to its own communications buffer. We'll need to read all of the bytes from the buffer and shift them left if necessary. These bytes will come in an order where the most significant bytes will come first and the least significant ones will come last. This layout is also defined in the datasheet as per order of the registers. That means as each byte is received, all the previous bytes we had received need to be shifted 8 to the left. So here we'll be using this logical OR, which is right here, on the current running total with the newest byte. So this ensures all of the data is combined correctly and no bytes are lost. Finally, we return our value from the function. Note that this value is stored in a 32-bit or a 4-byte integer. This means that we can store at most 4 bytes, so we can have either 1, 2, 3, or 4 bytes via our numbytes variable here. And this is enough for all the measurements necessary from the BMP180. However, it's important to note that other sensors may require different setups. Now, what I've done here is I've created this function, group addresses. Now this also loops back into our void loop function here. Now let's see what this group addresses one does. So we're essentially defining where our register values are. So these are all different addresses. So we have 0AA, 0AC, 0AE. But after AA comes AB, after AC comes AD. So what this does is we're actually reading in 2 bytes, AA and AB in this line. And in AC2, this variable is reading AC and AD. AC3 will be reading AE. That's what the void group addresses function is doing here. Now what we'll do, we'll actually define our uncompensated temperature value. Now the wonderful thing about this datasheet is it tells us exactly how to go about this. So let's take a look at this. So on this flowchart on page 15, all of this is defined. So first we have read in our calibration data. Now we'll want to read in our uncompensated temperature value. So the very first step is to begin transmission with our BMP180 address. Remember, this actually means the 0x77 address we found with the I2C scanner. So first, what this flowchart is telling us is to write 0x2e into the register 0xF4 and wait 4.5 milliseconds. So we've written 2e into F4, and we are ending the transmissions and we're waiting for 4.5 seconds. Now it's telling us this UT, so this read to register function we will be plugging this into, and below we will be calculating our temperature value. So that's what this two temperature boxes, I've just grouped this in together. So we have our read uncompensated temperature value and the calculations all in one function. So we have x1 and it's saying UT minus our in32 AC6. So we've done all of these formulas here, and we can move on to our read uncompensated pressure. Essentially, we're following the same format here with the wire.begin transmission for the BMP180's address, which is 0x77, and we are following this flowchart. So we're writing into the F4, and we're also writing into the 34. And as you can see in the flowchart here, it's telling us to write into 34 and shift over 6 and wait. So we have our conversion time delay, which is what we set our resolution rate as, and we have ended the transmission. So also the same thing as I've done in the temperature function, I have just plugged in all of these formulas and conversions so that we can output our actual pressure value, which is right here. So our pressure value is output in pascals, but I've converted into hectopascals with P divided by 100, and we've returned P. So it's important to note that in our UP row here, this is actually reading 3 bytes. This is reading our MSB, LSB, and XLSB. This is why we had the numbytes variable created above. So for temperature, we only needed the 2, the MSB and LSB. However, for the pressure, we actually needed 3 of them, the MSB, LSB, and XLSB. You can see this right here. So they're asking us for the MSB, LSB, and XLSB. So what I've done now, since I've made these two calculations functions, the pressure and temperature, I can just call these right into my void loop, and they'll continuously refresh with new data, and they'll constantly output this into our serial monitor. So let's upload this code and see how it works. So you can see our output here. It's about 70 degrees Fahrenheit in the room I'm sitting in. The pressure is 951 hectopascals, and our altitude is 143 meters. Now you can have these in any units you want. You just have to add some conversion factors. But this ends the coding portion for our BMP180 sensor. Let's move on to our MPU9250.